The work energy theorem. Solving problems using Newton's second law to find speeds can be difficult if the forces involved are complicated. An alternative is to relate the speed of an object to net work done on it by the resultant force. So let's see how it works. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. For the sake of simplicity, to get a relationship between net work and the speed given to an object by the resultant force acting on it, we will consider the case in which a particle with mass m is moving to the right under the action of a constant resultant force F, as shown in the diagram. The force produces an acceleration A given by Newton's second law. Let the initial speed of the particle be u. Because we have acceleration, the speed will change. Let the speed be v after traveling a distance d. As the acceleration is constant, we can use this equation from kinematics for the change in speed over distance d. Solving this equation for acceleration gives the work done by the net force F is calculated as the product of its magnitude and the particle's displacement. When the acceleration is substituted into the expression for net work, we obtain this expression. Cancelling d, we can rewrite this as follows. The quantity 1/2 times mass times speed squared is the energy the particle has due to its motion, called kinetic energy. For speed v, kinetic energy is defined as follows. The previous equation is known as the work energy theorem. The work energy theorem states that the work done by the net force on a particle equals the change in the particle's kinetic energy. Let's see how the work energy theorem works. The combined mass of a cyclist and her bicycle is 65 kilograms. She accelerated from 6 meters per second to 12 meters per second and 80 meters along a horizontal road. Calculate the work done by the net force in accelerating the cyclist and her bicycle. Calculate the net forward force. The initial speed is 6 meters per second. After traveling 80 meters, the speed is 12 meters per second. We now relate the speed to the work done by the work energy theorem. The work done by the net force F is given by the change of the body's kinetic energy. That is, it is the final kinetic energy minus the initial kinetic energy. To find the net force, we use the network. The network is the resultant force times the displacement. Now we solve for F. Pay attention to the next example. Look at the diagram. When the driver slams on his brakes, the speed is 126 km per hour. But we must use a meter per second, so we divide the speed by 3.6 to get the speed in meter per second. The initial speed is 35 meters per second, and we take the final speed to be 0 just as the braking vehicle reaches the rear of the vehicle at rest. After the brakes are applied, a constant kinetic friction force acts on the car. We now calculate the net work, which involves just the kinetic friction because the normal and gravity forces are perpendicular to the motion. The work done by the net force is given by the change of the car's kinetic energy. The only force doing work is the frictional force, which acts in the opposite direction to the motion. Therefore, the friction force is the net force. The net force exerted on the car times the displacement of the car is equal to work net. The angle between the friction force and the direction of motion is 180 degrees. So we need to multiply by cosine of 180 degrees, which is -1. The change in kinetic energy is equal to the work done. Then we solve for F. Pay attention to the next example. For the sake of simplicity, we assume the only force doing working is the resistive force, which acts in the opposite direction to the motion. The work done by the force is defined as the product of the force and the distance moved in the direction of the force. Since the bullet is moving in the direction opposite to the net resistive force, the work done by this force is negative. We now apply the work energy theorem to get the magnitude of the resistive force. The bullet now loses all its kinetic energy penetrating the barrier. We apply the work energy theorem again. The change in the bullet's kinetic energy is equal to the resistive force times the distance penetrated. We solve for distance.